Hi, everyone. All right. What if we have x as a function of y? Equations of the form x equals f of y. This time, our inputs are y coordinates and our outputs are x coordinates. Now, the underlying theory of functions is basically the same. So for example, here, consider the squaring function. If you say f of y equals y squared, that indicates the same function as f of x equals x squared. I could say f of grandma equals grandma squared. In both cases, f represents the squaring function. We assume the domain is all reals. Now here, if you think of f of y equals y squared, remember, we can replace f of y with x this time. Before, we replaced f of x with y. Now we're replacing f of y with x. Function values are now x coordinates. They used to be y coordinates. Okay, well, we can do a point plotting table for x equals y squared. Here's a point plotting table for x equals y squared. But this time, the domain consists of y values, basically. The domain consists of y values, basically. So you input various values for y. Domain is all reals. The input values can still be negative. And then we get corresponding squared values. So the square of 3 is 9. The square of negative 3 is also 9. So far, so good. This is very familiar when it comes to point plotting. But here's the difference. Here's where things change. Remember, the input values are the y coordinates. The output values are the x coordinates. So if the input y equals 3 yields the output x equals 9, the corresponding point is not 3 comma 9, it's 9 comma 3. You're still following the order x comma y. But remember, y this time is the input, x is the output. Likewise over here, the input negative 3 goes into the y position, the output 9 goes in the x position. When you point plot and connect the dots and extend, you get a parabola opening to the right. Now, remember, the squaring function is an even function. Notice the graph here is not symmetric about the y-axis, it's symmetric about the x-axis. So if you have x as an even function of y, you're going to have symmetry about the x-axis. Now, why didn't we see symmetry about the x-axis so often before? This is one of the few times we've seen symmetry about the x-axis. Well, because notice this graph fails what test? It fails the vertical line test. This graph fails the vertical line test. But that's okay, because we have here x as a function of y. We don't have to have the graph pass the VLT. However, we do need it to pass what? We do need it to pass the HLT, which is the horizontal line test. If you look at these horizontal lines, notice there is no horizontal line that intersects the graph more than once. 1 point, 1 point, 1 point, and so forth. This graph passes the HLT, the horizontal line test. Now, you can actually construct this graphs using, in a way, implicit functions. So what's another way of getting this graph over here? Well, we have x equals y squared. What if we turn it around? Y squared equals x. Apply the square root method. Y equals what? If y squared equals x, what could y be? Careful. Don't forget. Plus or minus the square root of x. Oh, and what happens if on Desmos we graph those guys? Y equals the square root of x. That's in red. How about y equals the opposite of the square root of x? That's in blue. Together, they form the graph of x equals y squared in green. It consists of this red graph over here this blue graph over here, together they form the green parabola opening to the right. All right. The horizontal line test. And then the graph may or may not pass the VLT. Now, as I mentioned before, when you do your point plotting, remember that your domain values are like y coordinates and your range values are like x coordinates. Before, when we had y as a function of x, domain was x, range was y. Now it's switched. Domain is y, range is x. Domain is y, the set of all real numbers. Range is x, the set of non-negative reals. Right. Domain corresponds to the y coordinates we pick up on the graph. Range corresponds to the x coordinates we pick up on the graph. By the way, odd functions still have the property that you have symmetry about the origin. For example, here's x equals y cubed. Solve this for y. What do you get? Y cubed equals x. Y equals the what? Y equals the cube root of x. So in case you're wondering how to graph x equals y cubed, it might help to solve it for y. And you better remember how to graph the cube root function. Y equals the cube root of x. These are equivalent equations. These are equivalent equations. And this indicates, by the way, that the cubing function and the cube root function are inverses. We'll talk about that later. Translations. How do we do shifting? This time, the easy shifts are the horizontal shifts or translations. When we had y as a function of x, it was easier to shift things up and down. That was back when we had y as a function of x, back in section 1.4. But now, in this section, horizontal shifts are easier, and vertical shifts are harder because they involve substitutions and the signs surprise. The things that made horizontal translations harder in 1.4 now make vertical translations harder in 1.8. So for example, consider the graph of x equals y squared. Let's do this on Desmos. Here's the graph of x equals y squared. This time, what happens if you add 2 to the right side? If you add 2 to the right side, you're increasing the x coordinates by 2. What happens then? You're shifting the graph to the right, because for each value of y, for example, y equals 0 here, the x coordinate increases by 2, in this case from x equals 0 to x equals 2. So for each value of y in the domain, you're increasing the x coordinate by 2 units. You're shifting the graph to the right. How do you shift the graph to the left by 2 units? X equals y squared, all minus 2. So this time, the horizontal shifts are easier. Red to blue for a rightward shift, red to green for a leftward shift. The horizontal shifts are easier. The harder shifts are the vertical shifts because they involve substitutions and the sign surprise. For example, to shift this graph up, you substitute with y minus 2. Let's do that. In red, we have x equals y squared. To shift up, it's x equals, you substitute y with y what? If you shift up, it's not y plus 2, it's y minus 2. That's squared. You shift up from the red graph to the purple graph. Confusing because it involves a substitution and the sign is surprising. The things that make vertical translations hard now made horizontal translations hard back in 1.4. The coordinate shifting method I mentioned before, where you replace x with x minus h and y with y minus k, that still works. Again, that's where you replace x with x minus h to shift horizontally, shift y with y minus k to shift vertically. That still applies. Reflections. Here's the key thing. The graph of x equals y squared is in blue. The graph of x equals the opposite of y squared is in red. That's a reflection about the y-axis. And why is that? In red, we have x equals y squared. X equals the opposite of y squared. Well, for each y value in the domain, look along the y-axis, what's happening? Each x coordinate becomes the opposite value from what you got before. So for example, when y equals 1, we have 1, 1 on the red graph for the original. We have negative 1, 1 for this blue point on the black graph. X equals the opposite of y squared. If x equals 1, if y equals 1, x equals negative 1. So for each y value in the domain, the corresponding x coordinate flips over to its opposite. For reflections about the x-axis, you do a substitution. Substitute y with its opposite, but those are more rare. Here I'm doing it to the square root function. X equals root y. You can skip the rest of the section, skim over it. The gallery, this is interesting, but I wouldn't expect you to know it off the bat. Next up, let's talk about inverse functions.